be here. All right, we probably will spread out between a couple of classrooms, but we'll do something. But be here, okay? It was designed as an hour exam. So you should have plenty of time. Because you have the entire 2 hours to take. All right, so time should not be an issue. What are we going to cover in here? Okay, the first topic is heat exchangers. You will have a question on heat exchangers. Or more. You should be able to deal with log mean temperature difference, as well as the NTU effectiveness method. Just like the homework problems, expect to calculate heat transfer convection coefficient. Okay? So that means you're going to have to go back to the second part of the block and figure out how to do that stuff, if you don't already know. So, you dealt with an annulus, you dealt with pipe flow inside, so you've got all those things going on. You should be able to do that. Okay? All right, so that's the first major topic. The second question, or questions, is going to be on radiation. All right, you should be familiar with the definitions. It's not beyond the pale that I might give you two surfaces and ask you to calculate how they see each other. You know, requiring some sort of little angle analysis like we did in the homework. Just a quick one, small problem. You should understand irradiation. Radiosity, emissivity, how those all work. You should be able to work problems with varying emissivities over different wavelengths, different spectral emissivities. And most certainly, you're going to have to, you will have to find view factors. The homework problems that you had, not this one that you're working on now, but the last 2 sets, were all problems from exams. All right? So ask yourself, could I do this? And if you can't, it's a problem. So you're going to have to find a few factors, and then you're going to have to solve for the heat exchange. Don't be surprised if you find a problem where you have to draw on your free convection, like in some of the problems on the homework, where you've got a surface and it's radiating, and you have to calculate the free convection coefficient, so that you find multi-mode heat transfer, convection, and radiation. Okey-dokey. Any questions? Where's Stuart? Stuart is not here. Huh? He's sleeping. So let me see if I can quote this right next time I see you, Jen.
Oh, don't tell myself.
Ali said that you just blew off the last class and slept in.
It's probably during
Tell
mechatronics.
him tomorrow.
What?
It's probably during mechatronics all night.
Till he wakes up.
Or fluids.
Alrighty, so we have Anthony and Jeb. Nobody sits between the two of you? No, between you two? Mitchell.
There's too many classes. You just move out now.
You what?
So you've missed too many by now.
Toss him under the bus.
Under the bus.
Toss him, sweep that kid under there.
Last class.
So I've got 3 people absent. And hold it, Abdul, 4.
Oh,
Pour some gasoline and light a match.
what?
Why?
It's like burning.
Are we bringing a little too much stress on the student body here? All right, okay.
Say that again. Oh.
Oh, okay, well, that's good. You're saved from the inferno. Just don't ask me.
I was gonna burn you.
Okay, now, let's turn to the example problem, shall we? Has everyone got all the view factors? Parts A, B, and C, pretty well done. Okay? Do you know how to do all these things? If you can do these, everything else will seem simple. All right, so now we need to do part D. This one is due at close business today. And while I won't say that I won't answer your questions, I'm not going to be very responsive. Because that's why I'm doing this now. And besides, I really have to get those damn labs graded sometime. So, all right. So part D. All right, so in part D, you're asked to write the system's equations for this configuration, solve for T1 and T2. Hint, the heater experiences both convective heat loss and electrical resistance. Heat in, neglect convective heat loss from the reflector. You need to solve for EB4, assuming the A4 is very large, and then obtain 2 expressions for EB1 and EB2. Substitute for EB2 to solve for EB1. Okay? Could be simpler than that. So let's look at node J1. Okay? So the first one will be node J1. So what is surface 1? Well, surface 1 is the heater. And what is the emissivity? It is 1. All right, so if I do this node, I have EB1, J1, J2, J3, and J4. Okay, 1 minus epsilon 1 over epsilon 1, area 1, 1 over A1, F1 to 2, 1 over A1, F1 to 3, 1 over A1, F1 to 4, or their reciprocity equivalents. All right, so what's the first thing that I can do here? Okay, now, I have to account for a couple of other things here. What else do I have to account for on this note?
Convection.
I have to account for convection. Which way is the convection going to go?
Out.
Out. So I've got, this would be Q1. This would be Q1 to 2. This would be Q1 to 3. This would be Q1 to 4. And we also know that there is Q convection out. Anything else?
Can I consider EB1 equals J1 since the necessity stuff?
That is correct, I can. Because epsilon 1 equals 1, EB1 equals J1. Okay? However, I got one more thing to consider. What else do I have to consider?
E4 is very large. E4 is very large.
Yeah, well, we'll take care of that, but that's, what? What comes into into the heater?
The electricity.
Yes, the resistance, the electric resistance. All right, so if I write what comes in, okay, so this node becomes EB1. So if I look at this, what do I have? I have Q, if I do a first law, I have Q electric 1 in, and everything else is out. This goes away because I don't have any electric resistance heating there, okay, or any surface resistance. So I have this, I have these four in, so I have Q convection 1 plus Q 1 to 2 plus Q 1 to 3 plus Q 1 to 4. Okay, this, so I have Q electrical 1 plus minus Q convection 1 equals, what is this going to be? This is going to be J1 minus J, excuse me. Except I'm not going to write J1, I'm going to write 1. EB1 minus J2 over 1 over A1 1 to 2 plus EB1 minus J3 over 1 over A1 F1 to 3 plus EB1 minus J4 over 1 over A1 F1 to 4. And while we're at it, what can I do to simplify this equation one more step? There's two more things I can do.
Multiply by A1.
Right. I can multiply by, well, yeah, but I'm not going to do that. That's just algebra at this point. There's something I can do to simplify this. I can make this simpler.
With J4 is the large.
Thank you. we can recognize the following. Recognize that A4 is very, very large, and therefore J4 is approximately EB4. What else can I do? Gotta look at the problem statement. You'll never have any luck with these problems. You can't solve them if you can't make the recognitions. What else do we know about this problem that's critical?
It's a long
What?
long
No,
rod.
it's re-rated.
Long rod is already E1, is epsilon is equal to 1, so EB1 is equal to J1. We started off with that assumption. What else somebody
The
said?
reflector is re-rated.
Which means
Um,
A2 All right, so now I'm going to rewrite these equations. So I'll have Q electric 1 minus the convective losses would be equal to EB1 minus EB2 over 1 over A1 F1 to 2 plus EB1 minus J3 over 1 over A1 F1 to 3 plus EB1 minus EB4 over 1 over A1 F1 to 4. So that is my first equation. Let's do node 2. All right, so I've already said that EB2, so we'll just write this like this. Now I've got a question for you. Is there any this would be 1 over A2 F2 to 1, 1 over A2 F2 to 3, and 1 over A2 F2 to 4. Now, question for you, is there any heat transfer going into the re-radiating reflector? Yeah, are we adding any resistance heat? Is there any convection from it? Well, in all probability, yes, but what does the problem statement say? What does it say specifically? Neglect any heat loss from the convector, or from the reflector, okay? So, that means that this equation is going to be Q2 to 1, Q2 to 3, Q2 to 4. So 0 is going to be equal to Q2 to 1 plus Q2 to 3 plus Q2 to 4, or EB2 minus EB1 over 1 over A2 F2 to 1 plus EB2 minus J3 1 over A2 F2 to 3 plus EB2 minus EB4 1 over A2 F2 to 4. Right? Am I making mistakes there? I don't think so. All right, let's look at node number. Let's look at node number 3.
Don't we already have enough information to solve?
You can do some solving, but you're going to need all 4 equations to solve the entire problem. All right, so we're going to get all 4 equations for you, set them up. Okay? So you have J3, EB3. This is EB1, EB2, EB4. This is 1 minus epsilon 3, epsilon 3, A3, 1 over A3, F3 to 1, 1 over A3, F3 to 2, 1 over A3, F3 to 4. Your heat transfers are Q3, Q3 to 1, Q3 to 2, and Q3 to 4. Okay? First law. Now double check, is there any heat transfer coming in to maintain the temperature of the plate? Anything leaving? What? What? The Q convection, right? That you calculated before. So we have Q convection 3 out. We have to take into account. So looking at the node, what comes in? Q3. What leaves? Q convection 3 plus Q 3 to 1 plus Q 3 to 2 plus Q 3 to 4, or it looks like this. You're going to have Q3, which is EB3 minus J3 over 1 minus epsilon 3 over epsilon 3 A3 equals Q convection 3 plus J3 minus EB1 over 1 over A3 F3 to 1 plus J3 minus EB2 over 1 over A3 F3 to 2 plus J3 minus EB4 over 1 over A3 F3 to 4. All right. Lastly, we're going to have, let me just make sure I get that right. One mistake. What mistake was that? What is the temperature of the plate? Go back to what you calculated before. Calculate the panel's radiosity. Recognize that the convective heat loss from the constant temperature plate is equal to the heat transfer associated with the surface radiated resistance. Okay? So what that means is that this has got to equal that if we're going to do what?
Have a constant.
If it's going to be maintained at constant temperature. So this has got to be and that is convective out, going to be out. And so this is going to be, it's going to be this, but this is going to be out, so it's going to have to be a negative number when you put it in, okay? It's going to be a negative number because it's really going out if all of these are positive. All right, so lastly, we have EB4. All right, so if we draw this, EB4 is going to be re-radiating, so it's not going to, even though it's going to see itself, it's not going to have any net heat exchange with itself. So we'll have heat exchange with these three surfaces, and here we're going to do something a little different. We're going to say that this is equal to A1 F1 to 4. This is 1 over A2 F2 to 4. And this is 1 over A3 F3 to 4. And why do we do that? Because we have no idea what A4 is. Okay? So we're just going to use reciprocity to put in these values. And so we're going to end up with 0 equal to Q4 to 1 plus Q4 to 2 plus Q4 to 3, or 0 is equal to EB4 minus EB1 over 1 over A1 F1 to 4 plus EB4 minus EB2 over 1 over A2 F2 to 4 plus EB4 minus J3 over 1 over A3 F3 to 4. All right, now, I'm not going to do the entire problem and give the answers to you, but those are the equations that you need to use to solve. And as Scott has already pointed out, you got enough information right here to solve for some of those unknown values. What do you know? Well, you know the temperature of the plate, the panel, that's 400 Kelvin. You know the temperature of the surroundings, that's 300 Kelvin. And that's going to give you enough to solve for temperatures T1, T2, and you're going to need to solve along the way for J3 as well. Okay? So you're going to solve for T1, T2, and do we solve for J3? Pardon me?
Actually solve for J2 part B.
Oh, yeah, you did already, that's right. So now you've got everything, you've got everything you need to solve. So all of these things come down to numbers. You've got these 4 equations and how many unknowns?
4.
Nope. EB2, no, excuse me. EB3 and EB4 are known. J3 is known. So you have solve for Q convection 3. So you're going to need to solve.
J3 is known.
Yeah, you solved for it in part. Solved for it in part B. Okay, that's right. I forgot about that for a moment. All right, then the heater itself, you've got to take into account. You got the resistance, electric, but you got to take into account the convective. So what are you going to model that as?
Constant time.
It is going to be constant temperature. It is maintained. We're assuming that it's constant temperature. But you're going to model it as a very long horizontal cylinder, okay, exposed to the air at 300 Kelvin. You're going to have to make a guess about, you've already solved for the temperature at 2, all right? So you can model what the, temperature of 1, excuse me, let me see here. You've already solved for the temperature at 1 by this point. So you solve for the temperature at 1, you know the ambient temperature, you're going to use the film temperature, you're going to come up with a free convection correlation for the long horizontal cylinder, and you're going to solve for the H, and then you're going to calculate what? This value right here. All right, so you're going to come up with that. So you're going to do all of that, and let's see. Calculate the free convection, that's the next one from the heater, and the loss through free convection. And then you're going to have to go back to this and calculate what? You're going to have to add it all up and use that to calculate the power. That is the problem. Okay, it's actually, it's an interesting problem. Much more difficult than you're ever going to get on an exam. Is that a question? No, really?
Yeah, no.
It really wasn't a question?
No.
But you're doing this.
Oh, I'm sorry.
Okay, I thought, don't go to an auction. You ever been to an auction? If you've ever been to a serious auction, the one thing you don't want to do is scratch your nose or do anything like this, or they'll, I'm not bidding, you know, and it'd be very embarrassing to be saying, I don't have any money anyway. Any movement of your hands is enough to get it. So, that's it. I got nothing more to say, like Forrest Gump. That's all I have to say about heat transfer. Okay. Now, let me see a hand. How many of you have done the online course survey? How many of you can be believed? Well, at least I can believe you guys. You haven't done it. All right? What are you going to do right after this class?
Thought we were going to do it in class.
I've got enough here. I don't really care. But I want you to go do it, all right? I want everyone's opinion. All right, to that end, I'm passing out the course entry sheet that I asked you to fill out. All right?